yesterday in the PowerPoints, we had that area of the cylinder exercise, and I said that, you know, this slide, one of you guys brought up that the slide looks wrong, and it's like been wrong for a couple of years, and I keep going back to the slide's author and saying, wait a sec, what's up with this? Okay, why doesn't this look right? Okay, well, it turns out that when they wrote the slide, they forgot the second half of the area formula. Okay, so the actual formula is 2 pi r squared, and I forget who asked that question, but you were really right to ask the question. And also height, then added to the height by 2 pi r squared. So again, we do the area of both upper and lower circles, and then we do the area, the perimeter area. So it actually came out to, they had the first part of it right, but they forgot the second part of it. Adding it together, it came up to 44521.60 square inches. And of course, we have to divide by 144 because most of everything we do with building dimensions and stuff like that is in square feet. Now, having said that, that is the area of the entire perimeter of the cylinder. But if you're just looking for the footprint, in other words, if this would be a circular room in a building, like an auditorium or something like that, if you were doing a circular room in a building, you would just take the area of the bottom circle. Okay? Does that make sense? Because we're really worried about floor space. So the only time you use the area around the perimeter area is when you're trying to like insulate something, insulate a water tank or something like that. So we really just, again, the area of the footprint is what we're mainly after. But again, whoever asked, I forget who asked the question yesterday, one of my night students actually, before I had a chance to, one of the night guys who listens to these lectures for their course, before I had a chance to actually look it up on my own, he sent this to me last night around 10 o'clock at night. So, again, good call on whoever caught that. It worked out good. So, anyway, I want to today a little bit talk about some of our heat load stuff. I said I was going to start talking about the spreadsheet that I gave you all to download. Okay, because we do want to start a little bit taking a look at this spreadsheet. Now, the spreadsheet has many sections when you look at it, and all this is a tool. You can do the same thing on paper, but it's so much easier to do it in an Excel spreadsheet, and it gives you better results. So what we're doing is you're going to put your project name, which is basically your name, under project. Okay, then there's a drop-down list over by design state. Okay, I've selected Florida because that's where I'm at, but you would want to come down to Pennsylvania, and then you'd want to select the correct county in Pennsylvania or the closest city, and they do actually have York listed. And that will set the weather and the temperatures properly here. We normally cool to a 70-degree indoor environment during heating season and air condition to a 75-degree indoor environment. We do put a design cooling relative humidity in here. You can change that down to 45%, which I probably would do, but anything under 50 I'm fine with. Any of the cells that are white, you're actually able to change. Okay? So that is your location information that you're going to have to set if you use this spreadsheet. Then what you're going to do, the next step you're going to do is you're going to come across the top of this, and in the white areas, you're going to type the names of all the rooms, like master bed, master bath, and you're just going to go across the top of it in the white areas, and it scrolls. And you're going to type the names of the rooms all the way across. Okay, now, The rest of this is where we start having to use our tables. So yesterday we did talk a little bit about walls and doors. We're going to talk about walls and doors a little bit more. Okay, but down at the bottom of the spreadsheet you have tabs for glass, doors, walls. Okay, if we take a look at glass, which is your windows, and let me pull this up a little bit in size so you can actually see it. Okay, you have two tables here. Okay, you have, it's going to say enter construction number, glass type, number of panes, and you're going to take a look to fill this out at the table 2A and 3A that I've given you. Remember I gave you those tables to download yesterday? Table 2A and 3A gives you the information. So for your house, you're going to find the type of glass and you're going to find the U values, okay, for heating, and you're going to find the cooling HTMs which are on those tables for each type of glass, and you're going to fill them in. Now, if your house has more than like 7 different types of glass, okay, which might be possible in older construction, you may have to jump down a little bit, and you can actually use these lines in skylight heat loss and stuff like that. But so you're not going to enter every window here. You're looking at window types. And you can also use that quick cheat sheet that I gave you on heating U values. I gave you one of basic construction materials. But I would really prefer if you were using the Manual J table 2A and 3A, because it actually gives you much better information. And here's two examples of how you're going to type this in. If you have skylights in your house or in the building you're working on, you can go ahead and enter the skylight information here. Okay, if you don't have skylights, leave it blank. Now, doors is basically the same thing, okay? Because again, we've already talked a little bit about doors and windows. We're going to talk about them some more today. But doors comes off table 4A, okay? And all you're going to do is type the door number, which is off table 4A, the type, the core insulation, and what I'm really after is the U value, okay? And this is only for exterior doors. Now, one of the important things to remember is if the glass in a door exceeds 50% of the door area, you classify it as a French door. Okay, so if the door has a glass pane in it, like a lot of front doors do, and if it's over 50% of the area, it gets classified as a French door. If it's under 51% of the door area, in other words, under 50, okay, you're going to classify it as a regular door, whatever the core insulation is. Take a wild guess if you don't know. Most front doors, most building doors, most garage doors will have metal or wood and will have an insulation sandwiched between the inside and outside metal. That's as far as I want you to go on this sheet, okay? Our next step we're going to do after you do the door and glass side, we're going to start taking a look at the first form, and you're going to fill in the net area for the different types of glass, okay? And you're going to put the direction in. So we're basically going to be dealing with what you've entered on those two tabs and the areas, again, for the doors and windows. Then, as one of our final steps, we're going to start getting into the walls. But the areas of the doors and windows are going to become pretty important here. Any questions on that?
I had a dumb question here. Where on Canvas can I find the Excel spreadsheet?
It's on let me point it out again. I did yesterday. Let me scroll up to that. It's on, I'm pretty sure, did I put it at the bottom of the plumbing plans? No, it's probably under the heat loss one. Bear with me a sec while I find it. Okay, there it is. It's under HVAC prints. It's under the module for HVAC prints that we did on April 3rd.
Okay, I see it.
You see it?
Thank you. Yep, got it. Thank you.
Okay, and you did, you know how to get into Excel if you don't have it downloaded already? Go to the
I downloaded it this morning. Yep.
Okay, cool. Okay, and you guys can download that. I think the licensing allows you to have it up to 4 computers, and we don't delete email addresses, so your Porter Chester email address stays if you need to use the EDU to renew it in the future. So, okay. So any other questions on those 3 tabs that I want you to start looking at? The first one, which the location information, the doors, and the glass, is where I want you to start looking at. And again, that goes into the parts 1 and 2 of the design project I've already had you working on, because you're actually gathering this information with the blueprint and then calculating the net areas. Okay, so I am going to jump into the PowerPoint for today. We're going to basically start where we left off, which is we were about to start talking about location information. Okay, and again, I will definitely make these available as I did yesterday. If you look at yesterday's module, these are available for download, but it's a lot easier if I do it at the end of the lecture than before, because I don't know how far I'm going to get in any given day. Let me just open up the chat here so I can see if anyone's asking questions. Okay, location information is extremely important, okay, because it can result in differences between any given site compared to the nearest weather station. And I'm going to give you some examples of this. Elevation changes greater than a few hundred feet can significantly change the design conditions. Distances from large bodies of water, okay? For example, if you're in Philadelphia, which is closer to the coast, and then you're in York, okay, you don't have as much water around. The Philadelphia weather is going to be more tempered because the water takes time to change temperatures. Okay, so again, big difference when you're closer to a large body of water, okay, rather than inland more. We just determine design temperatures by the average temperature. Okay, we know there's 8760 hours in a year, so there's 2 tables that are used. One is the 99.6%, which is 35 hours per year, and then the 99% table, which is the 88 hours per year. You don't have to worry about that for this project because Manual J actually picks, I believe it's the 99.6%. So when you look at this map, Boston and Worcester are only 25 miles apart. Okay, so over here on the star on the bottom, let me grab my pen here so I can scribble on these things. Okay, is Worcester. Boston is over here. Why is there a big temperature difference in the design temperatures between the 2 areas?
One's right on the bay, the water.
Yeah, the water. Okay, the water temperature makes things mild. And somebody has a lot of background noise off of mute, so just be aware of that. Okay, what about Grand Rapids and however you pronounce Muskegon or whatever it is? They're 30 miles apart, but there's a tremendous summer time difference or temperature difference. Okay, Grand Rapids here. Muskegon is there. What's affecting the temperature differences there?
Once again, the water, the lake.
Yeah, and there's something else very important. Here in the middle of a city, you're going to have a lot of concrete. You're going to have a lot of solar absorption. Okay, things are going to heat up faster because it's in a metropolitan area. Up here, it's sort of no man's land. There's probably a bunch of cottages up here and stuff like that. but there's not a lot of concrete in this area. So not only is the water affecting it, but the lack of concrete or blacktop in absorbing heat. So again, 30 miles apart or less, you can have major differences in design temperature. So it's always important to reset that location information. Okay, how would a house with trees and bushes compare to recorded wind speeds? Okay, a house that has trees and bushes is going to have wind breaks. The house is going to get less wind on it until the tree blows over. Okay, because there's a wind break. There's a break into wind. How would local hills and valleys affect the actual wind speed at a site? Same thing. You have wind breaks. Especially if you're at the top of a hill, you're going to get all the wind. If you're in a valley, you're going to get less wind. How would recorded wind speed compare to the actual wind speed at the top floor of a tallest office building in town? You have to look at stuff like this. Okay, recorded wind speed is not at the top of an office building. It's maybe 10 feet off the ground. You go to the top of one of the buildings in New York City or even in Philadelphia, you're going to have a different wind speed at the top of the building than at the bottom of the building. All of this stuff has to come into play with load calculations, specifically infiltration is what we're talking about here. Infiltration is very important because when we start looking at the composition of walls, okay, there's different substances in the walls. Remember I told you yesterday that when you take a look at an outside wall, okay, we know that we have an air film that develops on the inside of the wall. Then we have our gypsum, that's our sheetrock. Then we have a wood frame. Then we have insulation. Then we have sheathing. Then we might have wood siding. And then, believe it or not, there's a little air film that develops on the outside of the wall as well. Okay, all of that is our wall added together. So you add it all up, you find out our total thermal resistance, that's our R value, is 14.3. Okay, on the cavity. Then again, we have the framing. Okay, all of these go together. That's a composite wall. So when you're looking up tables in the Manual J, this is all actually put together for you when you're looking at the wall tables, because it's going to ask you what the wall's made of. But all of this goes together and provides a thermal break. Now, when you're looking at this, okay, why is the framing so much lower than the cavity? Okay, when you look at this, why is the framing so much lower? The frame, or I'm sorry, the framing is 7.7. The cavity is 14.3. Why is it so much lower?
Because there are studs where there's insulation in the other part of the wall.
Right, there's a thermal bridge. That wood stud, even though it has some resistance to heat transfer just because it's wood, it's still a thermal bridge between the indoor and the outside. It's two parts touching.
It's interesting. They even make insulated studs now.
Do they really? I haven't seen that yet.
Yeah, they're kind of broken up, and they have bits of insulation ran through the stuff. Pretty interesting looking.
Wonder how the off-gassing goes with that.
Yeah, I'm not sure.
Okay, so again, these two little red arrows that just popped up, it just shows you the direction of wind and airflow. This is on a cold day, or this is on a situation where the heat is trying to escape the house and go outside, okay? Because we're going from indoor to outdoor. Okay, now, we could have a metal stud. Look at the difference between the wood stud and the metal stud. So which allows more heat to travel, or which allows more heat flow, the wood or the metal? It's the metal. Look at the R value. The wood stud has an R value of 4.38. My metal stud has an R value of 0. That's sort of bad. So in residential construction, would I want to put, or actually commercial construction as well, would I want to put a metal stud on an outside wall? Probably not. Okay, but they do it in commercial construction all the time. They're not really worried about the amount of energy lost there. It's more ease of the building. Okay, so just a comparison to show you. Okay, what's a thermal bridge? Someone give me an example of a thermal bridge. Come on, folks. Thermal bridge, what is it? Give me an example.
Would that be that infrared picture you showed us with the beam?
Yeah, like a large metal.
The steel beam. Okay, steel beam would be a thermal bridge. It's basically any substance that allows a path for heat transfer without going through insulation. It's something that connects the indoor and the outdoor environment. Okay, steel beams in remodels are the biggest one of them. But what about our metal studs from this past slide? Is that a thermal bridge?
Yeah.
Yes, anything metal in the structure is a thermal bridge.
Yeah, is my wood stud a little bit of a thermal bridge?
It can be.
Yeah, depending on the temperature difference between the indoor and the outdoor, there's no insulation for plain wood stud. And I do got to go find those insulated studs. I got to go look at those as soon as I can get into a store. So, yeah, thermal bridge is any substance that allows a direct connection between an inside wall and an outside wall and allows heat to flow through it. Okay, now, slab-on-grade. Okay, slab-on-grade construction. I don't know if any of you have it, okay, or if most of you have basements, but slab-on-grade is basically concrete basement floor or concrete floor without a basement where it is sitting right on the grade, okay, in other words, nothing under it. Slab-on-grade is a basement floor, but again, slab-on-grade construction a lot of times is without a basement. Okay, heat flow through an insulated concrete basement floor with a temperature difference of 20 degrees between the basement floor and the air 6 inches above it is 2 BTU hours per square foot. Okay, it's a guesstimate, but it's usually right. So if any of you are doing on your heat loads and have a slab floor, concrete floor, okay, without a basement, or if you're including your basement on a heat load, your slab on grade is 2 BTU hours per square foot per degree Fahrenheit. Okay, that's a magic number. Use it. Okay, for smaller floor areas, you take the length of the exposed edge. Okay, basically you measure the perimeter around the floor. That's all concrete. You take the length of the exposed edge, multiply by 0.81 times delta T. Okay, and that gives you your Q value. That's your heat loss. So here, instead of using area, you are using the perimeter around the concrete floor. Multiply by 0.81, and then that's your delta times your delta T, which is your temperature difference, and that gives you your heat loss through the floor. For large floors, you take basically that have a 10-foot width around the perimeter. This is a big commercial building. You take the length of the exposed edge, again, okay, and then you do the 0.81 times delta T, but then you add in the area of the rest of the floor, okay, with the exception of the 10-foot width. Okay, so you take the area of the rest of the floor, and it comes out as 2 BTU per hour per square foot. Does this sort of make sense when you look at it? Okay, for larger floors, we're basically doing a two-step. This is for large commercial buildings. For small floor areas, you can stick with the smaller that you don't worry about this 10-foot width and you don't worry about the area. Okay, basement floors, it's without any edge insulation. Slab on the concrete slab construction, no basements, use this. And again, that's heat loss. So here we have a slab on grade. It's 80 by 100, so we're talking 800 square feet. Okay, the delta T is 74 degrees. It's a pretty big delta T, actually. Okay, difference between indoor and outside, 74 degrees. Okay, so it's 800. Now, because this is such a large floor, you're going to come in 10 feet. So instead of 80, you're going to have 70 as our area there, and instead of 100, you're going to have 90. Because again, we're coming in our 10 feet. And this is, I should have drawn that up around there. Now, this is my perimeter measurement. You take your length all the way around the perimeter. Okay, that's step one. Step two, you take this area that is now 70 by 90. So the calculated total exposed edge is 360 feet. That's my edge all the way around. Because you have two sides of 80, you have two sides of 100, that's 360. My heat loss through the exposed edge is the perimeter times 0.81, just a magic number, believe it, times my delta T. And this is in BTU per hour, 21,578. That starts getting up to be a lot of heat loss. Then you have to calculate the interior area. That's this. Okay? And they do it a different way. They basically took it off two sides, okay? And they took their 100 minus 20, okay, and 80 minus 20. I was going to take it off both sides. So you have your 4,800 square feet, because again, we're coming in 10 feet here, we're coming in 10 feet here, we're coming in 10 feet here. So you're calculating your interior area. Question?
20 from 100 isn't 60.
No, but it's 80 from 20. 80 minus 20 is 60, right?
Oh, my fault. I'm looking at it wrong. Never mind.
You see it? And then the 100 is this, or the 100 minus 20 is that across.
Yeah, I looked at it wrong. Okay.
Loss through the interior area is my 4,800 times 2 is 9,600 BTUs per hour. That's my heat loss for the interior area. So my edge always has a larger heat loss unless I have insulation around the edge than my interior area, again, because of infiltration, airflow. Add the two numbers together. So my heat loss for my basement alone is 31,178 BTUs per hour. So if you have 100,000, if your house or a customer's house you're looking at, if they have 100,000 BTU furnace installed and they all of a sudden want to add ductwork to the basement, okay, and let's say the rest of the house is sized about 90,000 or 95,000 BTUs, and they want to add ductwork to the basement to heat and cool their basement, will it work? Again, if the house has 100,000 BTU furnace in it, okay, so my house has the 100,000, and I'm just going to use K. Everyone knows that means 1,000, okay, and my rest of my house is sized at 90,000. They left a sort of a wiggle room of 10,000 BTUs. Can I add ductwork to a 31,000 BTU basement?
No, you wouldn't want to do that.
Yeah, that would probably be a bad idea. They'd never be happy. Their house would never heat up on a cold, cold winter day. And I can guarantee that's going to happen when you're on call and nobody else is on a winter night sometime. Okay? So now the other question is, when we're looking at a basement, why do walls in a basement have less of a load than the above ground walls? What's special about walls in a basement? Why does it have less of a heat load?
They have
You're right, there's brick, but what else is not around a basement wall?
air.
Ambient air.
Air.
Yeah, the air. What level is the frost line in your area? How deep does the frost go?
You got 6 to 8 inches or so.
Okay, yeah. So anything under that, whatever your frost line is, anything under that, the temperature maintains a relative between like a 50 and 60 degree year-round. The deeper you go, the more stable the temperatures are. So your basements don't tend to have a lot of temperature variances. So the combination of concrete block or concrete or brick or stone or whatever you have, plus the fact that the ground doesn't change temperatures that much, basements have less of a load than above ground walls. Do we have to worry about the heat load of a basement? Oh yeah, if you're going to heat and cool your basement. Cooling becomes really easy, but heating sometimes becomes a problem. Walkout basements. Does everyone know what or should I say, does anybody not know what I mean by a walkout basement? Okay, walkout basements, sort of built into the side of a hill. Okay, the basement has like sliding doors or whatever that goes out to a patio. 3 sides of that basement are in the ground. One side of that basement is regular construction, 2x4, whatever your construction is. Okay, how do you handle it? You handle 3 of the basement walls as a basement, and then you handle the one wall separately. There's 2 different construction types. Okay, basements interior are considered conditioned space if a minimum of 50 degrees is maintained over the course of a heating system. It's conditioned if that basement is maintained at a minimum of 50 degrees. In older buildings, the basement walls above grade is often not insulated. Okay, so a lot of times when people are heating basements, the basement wall that's above the grade is not insulated. Okay, now where do they put the water pipes for outdoor shutoffs? Right above the basement wall, right above the brick or whatever that your basement was made of. That's where they run the water pipes. Okay, again, that's why those pipes freeze so easily. But the top of the basement walls is the biggest heat loss in a basement because a lot of times they don't insulate them. Okay, so 3 numbers are needed to calculate basement heat loss. You have your basement floor, you have your below grade wall, and you have your above grade wall. All 3 of those come together. Okay. Now, to determine heat losses due to air exchange, there were 2 guys that estimated the air exchange rate for an uninsulated basement at 0.67. Air changes per hour. ACH is always air changes per hour under winter conditions. Again, this is a magic number that has been researched and seems to work. It's an estimate, but it works. The exchange rate in a crawl space, okay, not a basement, but was the area you have to crawl through under the house, is about the same. Okay, 0.67 air changes per hour. And as we start going through our spreadsheets, you'll see where that comes into play. Soil has an R value. It's a resistive thing. It's resistive to heat transfer. Okay, soil has an R10 value. That's moist soil. Dry soil is a little differently, but most soil is a little bit moist. It has an R value of R10. The soil averages about 45 degrees in the wintertime. Next term, when we talk about geothermal heating, you'll understand why we worry about that. But again, outside of your basement walls, once you get down a little bit under the frost line, you're going to be hitting the 45 to 50 to 60 in that range, depending on exactly where you're at in the time of the year. Okay? Now, in my area, it's quite a bit different. We have sand. Okay, remember, I'm sort of living on a sandbar, and my soil temperature, even down to the well level, sometimes in peak summers hits 80 degrees. So I don't have a lot of cool soil there. But, and then you go further north into Vermont, that soil temperature sometimes never gets above 40 degrees. But the average soil temperature under the frost line is about 45 degrees. With an R10 insulating value. That's the important part about what's around basement walls. Okay, R10 insulation plus the insulating value of the bricks. Heat loss to crawl spaces depends on how well it's treated and insulated. Okay, most codes require crawl spaces to be adequately vented year-round to minimize moisture problem. However, venting the crawl space during the heating season causes substantial heat loss through the floor. Floors always feel cold. My dad lives up in Vermont, and when he first bought his new condo, one of the things we had to do was go up and insulate the crawl space because all the insulation fell out and was sort of moldy too. But again, cold floor areas, if the crawl spaces are not insulated, tremendous heat loss. The temperature difference between the floor of a crawl space would be about the same as for exterior walls. Most crawl spaces, as it says, are not protected from the outdoor environment. They have to be vented. Air has to flow through them, or they start building up mold and mildew and other moisture issues. So crawl spaces, same difference as the exterior wall, basically. The rate of heat loss through the floor to a crawl space will equal the sum of losses to the ground due to air exchange through the vents and other perimeter walls. The temperature of the crawl space is somewhere between the outdoor and the indoor temperature. In other words, crawl space won't be as cold as the outdoor environment, but it's going to be someplace between the indoor and the outdoor environments. Under normal conditions, the crawl space is close to 55 degrees, and the losses to the ground, which is about 50-degree winter, become very small. But then again, you have the loss from the house that you're trying to maintain at 70 degrees to the crawl space. So again, there's heat loss all the way through. Crawl spaces are not all that great. As a service technician, you're going to occasionally have the opportunity to work in a crawl space, because that's where they install the furnaces. Okay, now again, furnaces at 55 degrees, you're fine. But if someone installs a high-efficiency gas furnace in a crawl space that drops below 32 degrees, the condensate is going to freeze up and you're going to have a service call. Okay, so again, it's very important to realize that these crawl spaces can freeze on really cold, windy days. Dormers, gables, and overhangs. Okay, gabled roof. Add several feet to the ceiling area and possible adjustments to the ceiling U factor because the construction details of the sloped section. Okay, so again, you might have a sloped roof and then a flat portion of the roof or a flat portion of the ceiling. Okay, sometimes you can just guesstimate what the actual addition of the area is over time. Sometimes you have to actually figure it out. Okay, too often insulation contractors leave gaps and holes in these hard to insulate areas. I've seen this a lot. Okay, when you have an inside vaulted ceiling that's sandwiched almost directly to the joists, your roof joists. Okay, sometimes they don't put insulation in there, especially if they do the sheetrock before the building inspector gets there. They won't see the insulation isn't missing. There's gaps and holes. And you're always going to get complaints from customers. What's the easiest way to tell if there's insulation missing on one of these areas? There's actually two easy ways. How would you do it? Anybody?
Can you repeat the question?
Yeah. When you have a vaulted ceiling that's sandwiched right up against the ceiling joists, contractors sometimes forget to put insulation between the vaulted ceiling and the roof. How would you figure out that the insulation's missing? 2 easy ways.
Would you feel the wall where it would be connected?
Well, yeah, I wasn't even thinking of that. You could get up on a ladder and feel the ceiling on a cold day to see if it, or a hot day to see if it either feels cold or hot. But there's another easy way on a winter day to tell if that insulation is missing. Should there be snow on the roof?
There should be, yeah. If it's not, then the heat's up there.
Yup.
Yeah. Melting the
Okay.
snow.
I could pull up to a house if the rest of the buildings around have snow on the roofs, and I can tell you if there's an insulation problem or a ductwork leak by looking at the snow on the roof. The other easy way is infrared cameras. Work really well. Moisture control within a wall cavity is important. Wet insulation has little insulating value. Remember that picture I showed you yesterday of what wet insulation does around a window? That's a reason for this. Moisture control is very important within a cavity because wet insulation has no insulating value. A heat loss summary gives the designer an opportunity to see if any of the calculated values are out of line. Okay, we can use the heat loss rate per square foot of a zone or floor area as a benchmark or reality check. When you do your spreadsheets, if you get a heat loss of like 1,000 or 2,000 BTUs per square feet, okay, we might need to take a check if it doesn't match the rest of the zones. Okay, so when you come over to when we're all done with this, when you come over to your bottom of your, you'll come down here to the bottom of your sheet for each room, okay, you'll find the sensible heat loss or gain. That will be the number that's filled in down at the bottom for heating and cooling. And if one of these rooms is way different and has about the same size, we know we've made a mistake someplace. Okay, so again, there's a reality check. Okay, and then you also have some summaries down here. But we'll get to that. But again, those summaries are really important because it gives you the ability to do a functional check. Okay, because you know what? Everyone's human. You'll make a mistake someplace along the way. So what we need to do is we have to identify the heating zones within a building. For each zone, in this case, I want you to think about, instead of the word zone, I want you to think about room. Okay, because we have all the different rooms. That's what we're going to be working with. Okay, so we're going to identify all the different heating zones within a building. For each zone, we're going to identify the exposed surfaces by direction and type. Remember, I've already had you doing this with your drawings. You've figured out what the walls, the lengths are. You've figured out the areas of them. You're working on identifying the types when we do the areas of the windows and everything else like that. And we're going to determine the net area. This is actually part 2 of your project. Okay, finding the net area of the different surfaces for each room. Then we're going to calculate the effective U factor for each surface, or we're going to look it up in the tables. I suggest using the tables. Okay, so for every net area, for each type of surface, there's a U factor. Okay, by the way, that's going to be part 3 that I haven't posted yet. But that's going to be on your spreadsheet. Then you're going to multiply across, and your spreadsheet will do this automatically for you, to get the Q, which is our heat gain or loss. Okay, so it's Q equals UA delta T, And then it's going to add down for the room to assemble all the portions of the room, walls, windows, doors, or whatever, and you're going to get the total heat loss or gain for that zone. That's what I just showed you at the bottom of this sheet. Okay, once you put in your net areas, select the correct construction type, it's going to calculate the heating and cooling BTUs for that area. It's going to add it down all the way, okay, and down at the bottom, you're going to find your total heating and cooling load for that room. Okay? That's our important thing, because we'll have a building total. We're going to have a block load that tells me what the furnace or air conditioning has to be signed at. But the room heat load tells me what each individual room needs, which allows me to put in the correct ductwork or baseboard heating or whatever you want to use in there. It allows us to size it properly. Okay. Question on that? Question on the process here? Anything? Okay. So heating loads, we try to keep conservative. We want to slightly overestimate the actual heating loss. Now, I don't mean large overestimate. I want to be within 10%, but I want to slightly overestimate the heat loss. Okay, that allows people to be comfortable on colder days. So by slightly overestimating, we're actually doing better for the customer. And I'm not saying overestimate by hundreds of thousands of BTUs. I mean, don't put in a boiler that could heat half of Chicago into a house that's 800 square feet. It probably wouldn't be a good idea. But 10% difference, you're fine on. Okay, remember, thermal bridges, short circuits around insulation. Why do I keep bringing up thermal bridges? Because they can really affect your heat load. You have to be very well aware of these. Now, heat gains are important primarily for cooling. Okay, heat gains from the sun and other internal sources within the building are neglected when doing heat load calculations, because we can't depend on these sources being available on cold winter nights. Okay, but heat gains we look at on the cooling side. This is your biggest difference between heating and cooling. Heat gains from sun, internal sources like copy machines, building components, windows, stuff like that from the sun. I don't worry about it for heating. I worry about it for cooling. Okay, remember a couple of you guys asked me if you need the outside dimensions or the inside dimensions. Okay, again, this is why I said inside is fine. Inside dimensions usually represent the best thermal conditions. Okay, it's more accurate because it's your inside area, inside volume we're talking about. Okay, we account for all areas of thermal loss when we start talking about walls. Don't go to a fraction of an inch. We want to go to our closest inch, okay? Don't do decimals if you can avoid it. Okay, we want to ensure that thermal energy is supplied at a rate that matches the rate of thermal loss. Otherwise, some areas become too warm and some areas become too cold. It's very important. Our our heating system has to be designed to supply heat at a rate that matches the rate of thermal loss. That's why we're going through this whole exercise. Cooling loads count lights, internal equipment, and solar gain, because at peak load, these are all on. An office building, peak load, 2 to 3 in the afternoon. A school building, peak load is whenever the building is occupied. Movie theaters, peak loads are when the movies are playing and you have large crowds. Heating loads cannot count on these loads because they're typically at peak loads, and these are not available, okay? So they're not always available for heating, so we can't count on them. For cooling, we include them. Any questions on that? Okay, unheated spaces. the temperature in unheated space between the outside and the inside spaces will always be a temperature between the outside air temperature and the inside. Okay, so if you have a, I think I had this diagram still up someplace, but if you have a, let me click over to my other sheet. If you have a detached garage, so if you have a house, get my box, there we go. If you have a house, and if you have a detached garage over here next to the house, okay, and if you have a room behind there, we'll say that this is my garage, I'll just put a G in it, it's unheated. Okay, so we have heated here, we have heat here, and we have unheated here. Okay, what that is basically saying is that the temperature, if my outside temperature, let's say, is 20 degrees, if my inside temperature is 70 degrees, my unheated garage is going to be a temperature someplace between the 70 and the outside temperature. The better the insulation in this wall and this wall, the colder my garage is going to be. Okay, because in a garage environment, that's usually the two walls that are insulated. If I have an unheated garage, it's going to be basically it's going to be insulated on the inside, but a lot of times they don't bother to insulate the outside wall. So if anyone ever wanted to heat this garage, you'd really have to check and make sure that outside wall has insulation, because it might not have it. Okay, so that's what that PowerPoint is saying. The difference between the unheated space will have a temperature someplace between the 70 and the 20. Okay. Any questions on what we've gone over so far today? Okay, I want to talk a little about windows and doors. Okay, fenestration is how it's referred to. You're going to find this referred to in all the documentation, all the Manual J documentation. It's fenestration. It includes windows, skylights, and doors. Okay, fenestration is an external wall of a building, any area which allows light to pass. Commonly used to refer to any opening, usually glazed, in a building envelope. Windows, skylights, and doors. Okay, especially if they have glass in them. Windows and doors lose heat at a much different rate than insulated walls. Okay, windows and doors can be your biggest rate of heat loss. Okay, gains and losses in fenestration are direct conduction through the glass or the frame. Okay, and or the door. The frame, if it's a metal frame, remember I showed you that cross-section of the frame yesterday, which was sort of a plastic or vinyl frame. If it's not a plastic or vinyl frame, that metal frame has tremendous heat loss. Okay, gains can also be by radiation of heat into a house, typically from the sun, and out of a house from room temperature objects such as people, furniture, or interior walls. Okay, so we radiate heat in two directions, but the primary one when you come in is by the sun. Air leakage through and around them. Very few windows are extremely tight unless they're brand new Energy Star capable windows. There's going to be heat loss and gain around the windows. So we have some pretty significant energy effects of fenestration. Okay, we can use daylight to offset lighting requirements. This happens a lot in office buildings. Okay, we can use glazing and shading to control solar heat gain to supplement heating through the passive solar gain and minimize cooling requirements. Okay, again, if we use the proper glazing, in other words, the film or the energy reflective films on the outside of the windows, and if we use awnings, heavy drapes, or shades, we can control solar heat gain, okay, to allow it in during the heating season and to keep it out in the cooling season. Okay? And a lot of the new energy efficient windows do exactly this. By using those strategies, I can make a big difference with heating and cooling. You can use glazing. That's just a reflective layer on it to minimize conductive heat losses. We can specify how air leak fenestration products, okay, we can prevent air leaks. Fenestration affects building energy use through 4 basic mechanisms. Okay, it affects thermal heat, it affects solar heat gain, it affects air leakage and daylight. Okay, we can use fenestration, that's windows, to provide natural ventilation. It can help reduce energy for cooling and fresh air requirements. You know, opening a window allows fresh air into a building. Okay, there's a National Fenestration Rating Council. They provide all the ratings. Okay, it's an accreditation place basically. It's a nonprofit organization that provides fair and accurate and credible energy performance ratings for windows and doors. Okay, it's a voluntary program that tests and certifies labels, windows, doors, and skylights based on their energy performance ratings. I'm going to show you the label of this next because it's actually pretty important. The label provides a reliable way to determine what a window's energy properties are and to actually compare products. Okay, this is a label that's on all new windows. Okay, the U factor that I'm circling now is pretty important. That's your U factor. That would be used directly in your heat loss formula. We have solar heat gain coefficient. We use this as another multiplier. Okay, and it's built into your spreadsheet, but we use this when it's facing the sun. Okay, if this window is getting direct sunlight, okay, there's an additional 0.32 that's used. Tells you how much air leakage there is. Okay, and it tells you how easy it is to see through it. And it tells you what the condensation resistance is. Okay, will there be condensate on it? But primarily, I'm worried about these top 2 when I'm doing my load sizing. That's where I'm worried about, the 0.35 and the 0.32. Okay, so when we're talking about windows, we have to talk about the UE measurements. We have to talk about methods of measurement and product certification. The R value for windows varies depending on the parameters like the number and spacing of panes. I showed you this yesterday. The frame type and the special treatments such as low E coatings and gas fills. Okay, you can always find this information online. Okay, Google is a great tool. Window manufacturers, okay, data you can use. And we're not going to worry about workbooks. I'm not having you do that because we're doing it as a part of your products. Now, Energy Star has a definition of windows. It's called an assembled unit consisting of a frame and sash component holding 1 or more pieces of glazing functioning to emit light and air. Okay, I don't know why Energy Star needed its own definition, because they could maybe. Okay, but the parts of the window we're worried about the frame. We're worried about the glass. We're worried about any grills that go through here. Remember I said something about thermal bridging? These grills that are here, if they're metal, can be a thermal bridge. We're worried about the window head. That's at the top of the window. What's it built out of? What's the material that's anchoring this window? If it's a steel beam, I have a possibility of a thermal bridge. We're worried about the window jamb. That's the outside components. What's it made out of? Is it metal? Is it wood? Is it plastic? We're worried about the sash. We're worried about the sill. A lot of times the sill might be stone or marble. might not match the rest of the window, has a different heat loss and heat gain. Okay, all of those components we're worried about a window, but you know what? The beauty is that the manufacturer will tell you what it is. It will give you the U value. That's why you want to use the manufacturer's information as much as possible. So does the manual J tables I gave you. Obscure glass is glass that provides a textured surface. Okay, you see this a lot on front doors. There's a textured surface that people can't just see through. You also see it a lot of times on bathroom windows. It provides low visibility but allows in natural light. Rough openings. It's a framed opening in the wall in which a window or door is to be installed. By looking at this, I can tell what the header is, right? It's wood. Okay, so I can right away know for my heat loss or heat gain that unless they put foam insulation over this, which they might, there's a possibility of some real heat loss and heat gain here. Okay, the ability of a product to absorb certain types of energy and radiate that energy through itself and out of a room. Emissivity. Okay, again, this glass will absorb heat from inside the space and it will radiate it out of the space if the outdoor temperature is cooler. Okay. Again, I'm not worried about you actually memorizing these terms because you really don't have to, but you should know what it is when you see it in a piece, when you see it in a write-up someplace of a window type. Solar heat gain measures how well product blocks heat from the sun. This is a big office building. They've used glazing on the outside of it to be reflective. Okay? Prevents heat, blocks heat from the sun. Sometimes they use a reflective glazing that sort of reflects the heat off. The lower the rating, the greater its abilities to block the sun. Okay, again, it's sort of backwards. The lower the rating, the greater the ability is to block solar heat gain. Solar heat gain coefficient measures the rate of heat gain from solar energy passing through a product. It's on a scale of 0 to 1. Again, the lower the rating, the greater the ability to block solar heat gain. This will be on the, this is on the window labels. Visible transmittance is the ability of a window to allow daylight into a room. Okay, now, because they want to make it easy on everyone, there are target numbers we want in different places. Okay? Different climate zones. The country is built up into climate zones. You have the northern climate zone, that's all in blue. You have the north central, you have south central, and you have southern. Okay, you guys are sort of right on the border almost between the north central and the northern. Okay, so if depending on your building office, they may want you to work for the north central climate zone or for the northern. Okay, probably if I were doing an install, I'd argue that for the I do my air conditioning for north central and I do my heating for northern. Keeps it safe in the middle. But every window has different target numbers for the different climate zones. This is built into building code. Okay, so you have to have different U factors for different climate zones. Okay, southern climates, you'll notice that my U factor, okay, is pretty high here compared with what I would call the northern climate zone. Okay, so they allow more heat to come through, but what about solar heat gain? The number's actually lower, so it sort of blocks more solar heat. Okay, so that's the difference of climate zones, because again, up here we don't worry that much about air conditioning. It's easy to cool. Down here we worry about air conditioning, but not about heating. So climate zones make a major important difference. Different types of windows. Okay, we have fixed windows, we have awning types, we have bay and bow, we have casement, we have double hung, we have single hung, and then there's a Palladian, garden, curved, sliding, and custom. All of these are different types of windows. Fixed, you can't open it. You're seeing these a lot in hotels and office buildings and schools these days. You can't open it. They want it to look like you can open it, but they can't open it. Awning, it's hinged at the top and opens outward like an awning. Okay, they are a lot of times placed above or below windows and over doors for extra ventilation. They're hinged at the top and they sort of open outwards. That's an awning window. Bay and bow, bay window. Big area of window sort of curves out from the house. Okay, they have different heat loads because this area here has to be insulated. Okay, so it's very important to watch how these are built. By the way, does this area increase your room square footage? The area inside that bay window, does it increase your room square footage? Anybody?
Yes.
Yeah, not by a lot, but it does. But the most important thing is that this is a big heat loss and heat gain. Okay, if this is on a southern wall during the summer months, you have a lot of heat gain. If it's on the northern wall during winter months, you have a lot of heat loss. There's really no two ways around this. Okay, casement windows. Okay, use a hinged sash that cranks to swing out to the left or right. That's a casement window. Double hung, those are the most frequently seen windows. Up or down, open or closed. Slides in a track, usually has a weight or a counterweight or spring on it to help it, to hold it in place. Single hung. Okay, only the bottom part is movable. In the double hung, the top can move as well as the bottom. Single hung, only the bottom is movable. Palladian. Okay, it's a large arched window flanked by smaller windows on each side. Okay, this one isn't showing up exactly right. Okay, but it might have a large arched top window up here. Comes all the way down. And then sometimes it's flanked by smaller windows on the sides of it. Garden windows look like miniature greenhouses. Believe it or not, these are more efficient than the big bay windows. They hang out more. They don't look like they have a lot of insulation, but most often these are built with triple pane glass to protect the plants in here. So if you have a choice between a bay window and a garden window, I would always choose the garden window. They actually are more efficient. Sliding windows, slides horizontally on tracks. By the way, the sliding patio doors are just larger versions of these. Sliding patio doors that are all glass are a larger version of these. Horizontally on tracks. Curved, you don't see these in residential as much, but one or more curved frame members. It's often used over another window or door opening. Custom windows, special shaped windows. These get interesting because a lot of times you have to break them into smaller windows. Okay, so when you're doing heat loads on these, you have to figure out two different areas. You can use you can use half a circle for the top portion and then a rectangle for the bottom portion. And you add it together to get your areas. Okay, because there's no real good formula to do all of this at one time. So take half of a circle, okay, and then a rectangle and add it together to get your areas. Okay, so a lot of that has to do with the type of glazing and the types of windows. Okay, you're going to need that information when you start doing your heat loads. You've got to be able to find the type of the window you're looking at in the tables. Okay, and we're going to spend a little bit more time on that tomorrow. Okay, glazing. Okay, we've talked about it a few times. We have single glazing, double glazing, triple glazing, dynamic glazing, tempered glass, and low E glass. All glazing is talking about is basically the number of panes. Single glazing, 1 pane of glass, single pane. Double glazing, 2 panes of glass in a window. Triple, 3 panes of glass. Okay? There's 2 separate gas spaces. Between each set of windows, there's a gas space. We haven't even talked about what the gas is yet. Okay, because it could be an insulating type of glass. Okay? This is by far starts becoming the most efficient types of windows. The triple glazed, low heat absorbing. Okay? You can add storm windows. So for windows equipped with a storm window, okay, it actually shows in the data, but you can also use a similar configuration but an additional plane. So if you have a double pane window with a storm window, okay, you now have a triple pane window when you do your heat loads. So again, some of you guys do have storm windows most likely on your windows. Just use an extra pane of glass. That tells you about the storm window. And that, I think, is where we are going to leave off on the PowerPoint today. There's only so long any one person can listen to Windows. So that's where we're going to leave off for today. We have a little bit more to talk about Windows, and then we can start talking about wall areas and what makes up the wall and how to do the heat loads of the wall. So let me turn off the recording so we can have some discussion.